You ever have something that you took really good care of just break, seemingly out of nowhere? Well, today we're going to pull back the curtain on the hidden science that actually predicts the breaking point for pretty much everything around us.
I mean, we've all been there, right? A metal chair leg just snaps. A critical part in your car suddenly fails. It wasn't like you dropped it or hit it with a hammer, it just wore out. So, what's actually going on there? Why do things seem to have this built in expiration date?
Well, the answer has a name: mechanical fatigue life. Think about it like this. Every single time a part gets used, it bends, it twists, it takes on a load, an invisible clock is ticking down. That total number of ticks, or stress cycles as they're called, is its fatigue life. It's this unseen countdown timer on, well, everything. So here's what we're going to cover. We'll look at that unseen countdown, dig into all the crazy factors that affect it, see how engineers try to nail down a specific number, and then look at how this all works in the real world. And trust me, it's way more than just a number.
Okay, so what actually determines how long that countdown is? You might think it's just about age or how much you use something, but it is way more complicated than that. You can almost think of a part's fatigue life like a person's health. It's not just one thing, it's this whole web of different factors all playing a role.
For starters, let's just talk about the environment. Something as basic as the temperature going up can seriously shorten a component's life. And then you throw in the fact that the load it's carrying is always changing, always varying. Yeah, that invisible clock starts ticking a whole lot faster. And then there's lubrication. This one is a huge deal. It's kind of the unsung hero here. If that thin film of lubricant gets too thin, the fatigue life just plummets. Seriously, keeping things properly lubricated is absolutely crucial for making them last. Now let's get microscopic for a second. Even the tiniest details, like how rough or how hard the surface of a material is, can be the very starting point for a total failure. These little imperfections that you can't even see, over millions of cycles of stress, that can grow into massive, catastrophic cracks. And, of course, the design itself is massive. We're talking about things like internal clearance, which is really just the teeny tiny space between parts, and how stiff a bearing is. These choices can make or break a component's lifespan. Getting that little gap just right is a huge part of making things last as long as possible. So you see, engineers have to be incredible jugglers. They're trying to balance temperature, lubrication, the surface finish, internal stresses, clearance, stiffness, even the specific type of impeller in a pump matters. It's this giant, incredibly complex puzzle with a ton of moving pieces.
So, with all that complexity, what's the goal? Well, for an engineer, the holy grail is to take all of that chaos and boil it down to one single, solid, reliable number. It's this huge quest for certainty in a world that's just full of variables.
And sometimes the models get amazingly specific. I mean, look at this. One calculation predicted a fatigue life of 7,527.26 million revolutions, down to the hundredth of a million. That's an insane level of precision, at least in theory.
But then, reality hits. For all that amazing math, you often get a report that says, well, we ran the simulations, but we can't actually give you a specific number. So that certainty engineers are chasing, it can be really, really hard to pin down. And just to make things even more fun, the way you calculate it matters a lot. Get this, for the exact same part, one model predicted a lifespan almost 1.7 times longer than another model. So same component, different math, completely different answers. What do you do with that? So a lot of the time, the best you can get is a relative answer. You'll see things like, this design improves the service life, but without any hard numbers. No cycles, no years. Sometimes just knowing that it's better is the only thing you can be sure of. Okay, so it sounds a bit messy, right? With all this uncertainty, how on earth do engineers actually get from a bunch of theories to a prediction they can rely on in the real world? Well, let's dive into the tools and methods they use to bridge that exact gap. A big part of it is just testing. Engineers will isolate one variable, like temperature, and see what happens. This chart is a perfect example. You can see clear as day how the fatigue life of these composite joints just tanks as the temperature goes up. This is the kind of real-world data that forms the bedrock of any good prediction.
They also don't just rely on one tool. They use different types of computer models to attack the problem from all sides. So for this one turbine bearing, you had one model saying it would last longer and another saying it would fail sooner. Now, the actual answer is probably somewhere in the middle. By comparing these different predictions, they can start to zero in on a more realistic range. It all comes together in this kind of practical, step-by-step approach. First, they start with the basics, using established industry standards and formulas. Then, they bring in powerful statistical models to handle all those variables we talked about. Next, they simulate real-world conditions, using data from something called Wöhler curves, which are basically charts that show how a material holds up under different levels of stress. And the final, crucial step, they compare everything, all the models, all the data, to fine-tune their prediction. And all this work, all this modeling, isn't just an academic exercise. It leads to real, practical actions you can take. We know that remanufacturing a part can give it a new lease on life. We know that getting that internal clearance just right is the sweet spot for maximizing its lifespan. And we know that something as simple as maintaining that film of lubricant is key to making sure things last. So, why do we go through all this trouble? Why does this complicated hunt for a number matter so much? Well, because it fundamentally changes the world we build and live in. If you take away just one thing from all this, let it be this. Fatigue life is not some fixed expiration date stamped on a product to the factory. It's a living, breathing prediction. It's dynamic, and it's constantly changing based on how something is designed, how it's used, and the world it lives in. All right, so let's wrap this up. We've got this unseen countdown ticking away on everything from tiny bearings to massive bridges. Predicting it is a super complex puzzle, and engineers use a whole toolkit of models to get close to the answer. But when they get it right, man, that's how we get safer planes, medical devices we can trust, and infrastructure that stands the test of time. And get this for an impact, doing this better, improving reliability, can boost environmental sustainability by over 50%. Think about that. Less waste, fewer things to replace, a better planet.
So I'll leave you with this final thought to chew on. What's the real end game here for engineering? Is the future all about chasing this dream of inventing some kind of unbreakable, perfect material? Or is it about getting so good, so perfect, at predicting the exact moment when the stuff we already have will finally, inevitably reach its breaking point?